This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai's studies. A link is in the description box below. Does the following series converge or diverge? Because I see factorials, I'm going to use the ratio test. The rules for the ratio test are based on the limit as n approaches infinity of a ratio, so a fraction, and the numerator is your sequence, but wherever you see n, you add a 1, and then divide by your sequence. And ratio and root test both come with absolute value, and that's equal to a limit, or in Rutgers we say rho, even though it's a p, but we pronounce it as rho. So if rho is less than 1, rho is greater than 1, rho is equal to 1, then this series converges absolutely, diverges, or the test is inconclusive, meaning try another test. So we're going to take the limit as n approaches infinity of this, but wherever we see an n, we're going to add a 1. That's going to be 2, n plus 1, n plus 1 factorial, n plus 1 factorial. And then here, this n is being multiplied, so we need to add a 1 to that n. So it's going to become 2 times n plus 1, and then this whole thing is being factorialed. And then this is this, and so we have to divide by a of n, which is this, or we could just multiply by the opposite, just flip the numerator and denominator. And because n is equal to 1 and all we have are n's, then this series will only contain terms that are greater than or equal to 1. So it will always be a positive series, so the absolute values can go away. Nevertheless, they go away because the absolute value of this is this. So technically we're still using absolute value, and because of that we have to follow these rules. And so at this step, always switch your denominators. And then here you can simplify this to be 2n plus 2 when you distribute the 2. And you switch the denominators because now you have things that are similar next to each other. So this can be split up to 2 to the n times 2 to the first power. These cancel out, so you're left with 2. Here you ask yourself, which is bigger, this or this? Well, I would say these are bigger. So expand these and leave these alone. So this is really n plus 1 times n. To get to here, you do a minus 1. So this cancels out, you get the n. So that's where this comes from. I know to stop here, so I'm going to add a factorial because this is what I see here. So if this is that, and this is the same thing, then these cancel out, and we're left with that. To simplify this, ask yourself which is bigger, the numerator or the denominator. This is bigger because here we have 2n, here we have 2n, but here we have 2n plus 2, so the denominator is bigger. Meaning we're going to leave what's at the top alone, and we're going to expand what's on the bottom because it's bigger. So the way we expand is we start with what we have, and then to get to the next thing, we do a minus 1. So 2 minus 1, that's 1. So we're going to do 2n plus 1. This is not the same thing as this, so I'm going to keep going. So 1 minus 1 cancels out, we're left with 2n, so the next thing is 2n. This is the same thing as this, so I'm going to end it with a factorial. So then I'm able to cancel these out, and I'm left with 1 over here. And I can distribute these over here and move the whole thing here. And because this is a rational fraction, I know that if I can tell which term has the highest power in the denominator, I can divide every term in the fraction by that term. But it's easier to tell when it's simplified, so let's go ahead and do that. So this becomes 4n squared plus 2n plus 4n plus 2. These sum up to be 6n, and always simplify up here as well. So that's going to be n squared plus n plus 1. So it's going to be n squared plus 2n plus 1. And then here I can easily tell which term in my denominator has the highest power. That's n squared. So I'm going to divide every term in the fraction by n squared. So this cancels out to be 4. This cancels out to be 1. This cancels out to be 6 over n. This cancels out to be 2 over n. So we have the limit as n approaches infinity of 1 over 2 over n plus 1 over n squared, 4 plus 6 over n plus 2 over n squared. Now you can plug in infinity for n. Infinity squared is still just infinity. And anything divided by infinity when it comes to a limit goes to 0, because remember, one whole divided into infinitely small pieces gets infinitely smaller, so small it goes to 0. So we're left with 1 over 4, which is less than 1. Because you're taking 1 and dividing it, so obviously it's going to be less than 1. So rho is less than 1, therefore this series here converges absolutely. But they didn't ask us if the series converged absolutely, they asked us if it converged, period. So let's start with the conclusion, and then I'll get to how we figure that out. So since, and then we just take the original limit, I erased it, so I'm going to rewrite it, which is equal to 1/4, which is less than 1. The ratio test implies that the given series converges absolutely, but again, we want if it converges or not. So this is where our number 2 tool in our toolbox comes in. The absolute convergence test says that if you have any series that converges absolutely, which we do have, then we can say that that same series converges. And absolute convergence implies convergence by the absolute convergence theorem. So the given series converges as well. And that is our final answer.